The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
In the last lecture, we discussed a number of general properties for systems, which, as you recall, applied both to continuous time and to discrete time systems. And these properties were the properties associated with a system having memory, the issue of whether a system is or isn't invertible. We talked about causality and stability. And finally, we talked about linearity and time invariance. In today's lecture, what I'd like to do is focus specifically on linearity and time invariance and show how, for systems that have those properties, we can exploit them to generate a general representation. Well, let me begin by just reviewing the two properties again quickly. Time invariance, as you recall, is a property that applied both to continuous time and discrete time systems, and in essence stated that for any given input and output relationship, if we simply shift the input, then the output shifts by the same amount. And of course, exactly the same kind of statement applied in discrete time. So time invariance was a property that said that the system didn't care about what the time origin of the signal is. Linearity was a property related to the fact that if we have a set of outputs associated with a given set of inputs, as I've indicated here with the inputs as phi sub k and the outputs as psi sub k, then the property of linearity states that if we have an input which is a linear combination of those inputs, then the output is a linear combination of the associated outputs. So that linear combination of inputs generates, for a linear system, an output which is a linear combination of the associated outputs. Now, the question is, how can we exploit the properties of linearity and time invariance? And there's a basic strategy which will flow more or less through most of this course. The strategy is to attempt to decompose a signal, either continuous time or discrete time, into a set of basic signals, and I've indicated that here. And the question then is, what basic signals should we pick? Well, the answer kind of is we should pick a set of basic signals that provide a certain degree of analytical convenience. So we choose a set of inputs for the decomposition that provide outputs that we can easily generate. Now, as we'll see, when we do this, there are two classes of inputs that are particularly suited to that strategy. One class is the set of delayed impulses, namely decomposing a signal into a linear combination of these. And as we'll see, that leads to a representation for linear time invariant systems, which is referred to as convolution. A second is a decomposition of inputs into complex exponentials, a linear combination of complex exponentials, and that leads to a representation of signals and systems through what we'll refer to as Fourier analysis. Now, Fourier analysis will be a topic for a set of later lectures. What I'd like to begin with is the representation in terms of impulses and the associated description of linear time invariant systems using convolution. So let's begin with a discussion of discrete time signals, and in particular the issue of how discrete time signals can be decomposed as a linear combination of delayed impulses. Well, in fact, it's relatively straightforward. What I've shown here is a general sequence with values which I've indicated at the top. And more or less as we did when we talked about representing a unit step in terms of impulses, we can think of this general sequence as a sequence of impulses, delayed, namely occurring at the appropriate time instant and with the appropriate amplitude. So we can think of this general sequence as an impulse occurring at n equals 0 and with a height of x of 0, plus an impulse of height x of 1 occurring at time n equals 1, and so that's x of 1 times delta of n minus 1, an impulse at minus 1 with an amplitude of x of minus 1, etc. So if we continued to generate a set of weighted delayed unit samples like that, and if we add all these together, then that will generate the total sequence. Algebraically, then what that corresponds to is representing the sequence as a sum of individual terms, as I've indicated here, or in terms of a general sum, the sum of x of k delta of n minus k. So that's our strategy. The strategy is to decompose an arbitrary sequence into a linear combination of weighted delayed impulses. And here again is the representation, which we just finished generating. Now, why is this representation useful? It's useful because we now have a decomposition of the sequence as a linear combination of basic sequences, namely the delayed impulses. And if we are talking about a linear system, the response to that linear combination is a linear combination of the responses. So if we denote the response to a delayed impulse as h sub k of n, then the response to this general input is what I've indicated here, where y of n, of course, is the output due to the general input x of n. H sub k of n is the output due to the delayed impulse, and these are simply the coefficients in the weighting. So for a linear system, we have this representation, and if now, in addition, the system is time invariant, we can, in fact, relate the outputs due to these individual delayed impulses. Specifically, if the system is time invariant, then the response to an impulse at time k is exactly the same as the response to an impulse at time 0 shifted over to time k. Said another way, h sub k of n is simply h0 of n minus k, where h0 is the response of the system to an impulse at n equals 0. And it's generally useful to, rather than carrying around h0 of n, just simply define h0 of n as h of n, which is the unit sample or unit impulse response of the system. And so the consequence then is, for a linear time invariant system, the output can be expressed as this sum where h of n minus k is the response to an impulse occurring at time n equals k. And this is referred to as the convolution sum. Now, we can, just to emphasize how we've gone about this, let me show it from another perspective. We, of course, have taken the sequence x of n. We have decomposed it as a linear combination of these weighted delayed impulses. When these are added together, those correspond to the original sequence x of n. If this impulse, for example, generates a response which is x of 0 times h of n, where h of n is the response to a unit impulse at n equals 0, and the second one generates a delayed weighted response, and the third one similarly, and we generate these individual responses. These are all added together, and it's that linear combination that forms the final output. So that's really kind of the way we're thinking about it. We have a general sequence. We're thinking of each individual sample individually. Each one of those pops the system, and because of linearity, the response is the sum of those individual responses. Well, that's what happens in discrete time, and pretty much the same strategy works in continuous time. In particular, we can begin in continuous time with the notion of decomposing a continuous time signal into a succession of arbitrarily narrow rectangles. And as these rectangles, as the width of the rectangles goes to 0, the approximation gets better. And essentially what's going to happen is that each of those individual rectangles, as they get narrower and narrower, correspond more and more to an impulse. Well, let me show you what I mean. Here we have a continuous time signal, and I've approximated it by a staircase. So in essence, I can think of this as individual rectangles of heights associated with the height of the continuous curve. And so I've indicated that down below. Here, for example, is the impulse corresponding to the rectangle between t equals minus 2 delta and t equals minus delta. Here's the one from minus delta to 0. And as we continue on down, we get impulses, or rather rectangles, from successive parts of the waveform. Now let's look specifically at the rectangle, for example, starting at 0 and ending at delta. And the amplitude of it is x of delta. And so what we have, actually this should be x of 0. And so let me just correct that here. That's x of 0. And so we have a rectangle of height x of 0. And recall the function that I defined last time as delta sub capital delta of t, which had height 1 over delta and width delta. So multiplying finally by this last little delta, then this is a representation for the rectangle that I've shown there. Now, there's a little bit of algebra there to kind of track through, but what we're really doing is just simply representing this in terms of rectangles. What I want to do is describe each rectangle as, in terms of that function delta sub delta of t, which in the limit then becomes an impulse. Well, so let's track that through a little further. When we have that linear combination, then we're saying that x of t can be represented by a sum as I indicate here, which I can then write more generally in this form, just indicating that this is an infinite sum. We now want to take the limit as delta goes to 0, and as delta goes to 0, notice that this term becomes arbitrarily narrow. This goes to our impulse function, and this, of course, goes to x of tau. And in fact, in the limit, a sum of this form is exactly the way an integral is defined. So we have an expression for y of t in terms of an impulse function. There, I have to admit, is a little bit of detail to kind of focus on at your leisure, but this is the general flow of the strategy. So what we have now is an integral that tells us how x of t can be described as a sum or linear combination involving impulses. This bottom equation, by the way, is often referred to as the sifting integral. In essence, what it says is that if I take a time function, x of t, and put it through that integral, the impulse, as it zips by, generates x of t all over again. Now, at first glance, what it could look like is that we've taken a time function, x of t, and proceeded to represent it in a very complicated way in terms of itself. And one could ask, well, why bother doing that? And the reason, going back to what our strategy was, is that what we want to do is exploit the property of linearity. So by describing a time function as a linear combination of weighted delayed impulses, as in effect we've done through this summation that corresponds to a decomposition in terms of impulses, we can now exploit linearity, specifically recognizing that the output of a linear system is the sum of the responses to these individual inputs. So with h sub k delta of t corresponding to the response to delta sub delta of t minus k delta, and the rest of this stuff, the x of k delta and this little delta, are basically scale factors. For a linear system, then, if the input is expressed in this form, the output is expressed in this form, again taking the limit as delta goes to 0, by definition, this corresponds to an integral, and it's the integral that I indicate here, with h sub tau of t corresponding to the impulse response due to an impulse occurring at time tau. Now again, we can do the same thing. In particular, if the system is time invariant, then the response to each of these delayed impulses is simply a delayed version of the impulse response. And so we can relate these individual terms. And in particular, then, the response to an impulse occurring at time t equals tau is simply the response to an impulse occurring at time 0 shifted over to the time origin tau. And again, as we did before, we'll drop this subscript h0. So h0 of t we'll simply define as h of t. And what we're left with when we do that is the description of a linear time invariant system through this integral, which tells us how the output is related to the input and to the impulse response. Again, let's just quickly look at this from another perspective, as we did in discrete time. Recall that what we've done is to take the continuous function, decompose it in terms of rectangles, and then each of these rectangles generates its individual response, and then these individual responses are added together. And as we go through that process, of course, there's a process whereby we let the approximation go to the representation of a smooth curve. Now, again, I stress that there is certainly a fair amount to kind of examine carefully there, but it's important to also reflect on what we've done, which is really pretty significant. what we've managed to accomplish is to exploit the properties of linearity and time invariance so that the system could be represented in terms only of its response to an impulse at time 0. So for a linear time invariant system, quite amazingly actually, if you know its response to an impulse at t equals 0 or at n equals 0, depending on discrete or continuous time, then in fact, through the convolution sum in discrete time or the convolution integral in continuous time, you can generate the response to an arbitrary input. Let me just introduce a small amount of notation, again reminding you of the convolution sum in the discrete time case, which looks as I've indicated here, the sum of x of k, h of n minus k, will have the requirement of making such frequent reference to convolution that it's convenient to notationally represent it as I have here with an asterisk. And so x of n with the asterisk h of n means or denotes the convolution of x of n with h of n. And correspondingly, in the continuous time case, we have the convolution integral, which here is the sifting integral, as we talked about, representing x of t in terms of itself, or as a linear combination of delayed impulses. And here we have the convolution integral, and again, we'll use the asterisk